This example provides a generalized mesh procedure given that we are dealing here with a circuit with current and voltage sources, including a dependent source. In particular, we have a case with a current source on the circuit perimeter and another one inside. The problem asks to calculate VA, and we will do that via the mesh currents. First step is to identify all the finite meshes. Remember that a mesh is a loop with no other loop inside. We identify a mesh as finite when there is no open circuit in the loop. Otherwise, the mesh current would be 0. Also, the direction of each mesh current is totally at your choosing. I suggest that you choose all currents clockwise or all currents counterclockwise for consistency. Next, we put voltage labels on all resistors. Remember that a voltage definition implies a label and a set of polarities, pluses and minuses. No label should be inserted on any source voltage or current type. Also, the 2 ohm resistor already has a label. Don't add another one on top of that. Now we will begin the mathematical portion of the procedure. The first thing we do when we have current sources in the circuit is to express their output in terms of the mesh currents. For the independent source, which is located on the circuit perimeter, thus belonging to only one mesh, we say I4 is equal to 10 amps. In other words, the mesh current is going the same direction as the 10 amp source, so they must be equal. The dependent current source is, on the other hand, shared by 2 meshes, I3 and I2. Thus we write I2 minus I3 equal to 6 VA. And we do that because I2 is flowing in the same direction as the source, and I3 is flowing against it. This represents the 2 possibilities when circuits have current sources. 1, the case that the current source is located in one mesh, thus on the perimeter. If the source is an independent source, we then know that mesh current. That's the case we have here. The second case, the current source is shared by 2 meshes. Then we simply get a relationship between the 2 mesh currents. In this case, we have a dependent source, so we say I2 minus I3 equal to 6 VA. That gives us a relationship between I2 and I3. You will note that I replaced the mesh current I4 by 10 amps. From then on, I'm going to assume that that mesh current is known. So I've taken it out of my list of unknowns. Our next step is to write Kirchhoff voltage law equation in the meshes without current sources. This is what I would call regular mesh. In other words, no current source in that mesh. In our problem, there is only one such mesh, mesh I1. Some comments about writing KVL equations. Typically, I pick a rotation. Let's assume we pick clockwise, the same orientation as mesh I1. I pick a rotation, and the first sign that I find as I'm going around the loop, I put it down as the sign of the voltage. For example, let's assume that I begin at a 5 ohm resistor. So I'm going to say minus V3 minus V1 plus VA is equal to 0. If I pick the other rotation, the counterclockwise rotation, and I also start at the 5 ohm resistor, it is going to be plus V3 minus VA plus V1 equal to 0, which is in essence the same equation. Now, this is an extra step that we didn't have to deal with when we were dealing with circuits without current sources. This is the case when we have a current source. It doesn't matter if it's dependent or independent, but as long as it belongs to 2 meshes, then we have to create what is called a supermesh. A supermesh is essentially merging 2 adjacent meshes, here I2 and I3. In other words, we consider those 2 meshes and we simply ignore the branch that is common to both meshes. So we make a larger loop that is the perimeter of those 2 meshes, and here I'm showing it in green. So we form that supermesh, and the next step is to write a KVL around that supermesh. In this case, minus VA plus V1 minus V2 plus 4 volt plus V4 equal to 0. And of course, we could do it in the other orientation as well. and we get the same equation. Now that we have our three equations, three unknowns, because now I'm looking at the I4 current that I'm showing as 10 amp as a known current, we go ahead and write Ohm's law, which essentially convert the voltage into currents, into the mesh currents, which are unknown. You have to be careful here when you have resistors that belong to two meshes. Anytime you do have that, you should pay attention to that. Also, you should remember the passive sign convention, that current enters the positive terminal, thus voltage is equal to resistance times current. For example, if we pick the voltage VA, or the 2 ohm resistor, then we say VA is equal to 2 ohm times I1, because I1 is entering the positive terminal, minus I2, because I2 is entering the negative terminal. And that basically is carried on in all these equations. We take all of these Ohm's law equations and put them into the two KVL equations, including the source equations, because we have the source equation for the dependent source in particular, and we have one KVL in mesh I1 and the KVL on the super mesh. These are the three equations. But we use the Ohm's law equations into those collect terms for I1, I2, and I3, and we get to our three equations, three unknown, and solving for the current I1, I2, and I3. And we get these values for these currents. And having solved for the currents, we can calculate easily VA, which is 2 times I1 minus I2, and the problem is solved. This example is as complex as it gets. I think it's a fair statement to say that if you can solve a problem of this complexity, in other words, you have 4 meshes here that you have to solve, and you have current source, voltage sources, dependent sources, I think these are the kind of complexity that you should be able to handle by the time you get into your exam where you're being tested on DC circuits.